Hello everyone, let's get started our force revision. Two masses of M, small mass 4 kg and large mass 6 kg are joined together by a string that passes over a pulley. This arrangement is known as outward smashing. The masses are held stationary and suddenly released. Determines acceleration of each masses. Intuition tells us that the larger mass will start moving downward and a small mass will go up. So if we say that the larger mass's acceleration is a, then the other mass's acceleration will also be a in magnitude, but of course in opposite direction. So two accelerations are the same because the string cannot be extended. The forces on each mass are weight, mg, and tension. So let's take a look at the small mass. The small mass accelerates upward direction. So the net force equals to m times a. That is T minus mg equals to ma. This is equation 1. Now let's take a look at the larger mass. The larger mass accelerates downward direction. That is mg minus t equals to ma. That's equation 2. Equation 2 plus equation 1, we get mg minus t minus mg equals to ma plus ma. Tensions cancel out. We get mg minus mg equals to, we can take it out the acceleration, and we also can take it out the g, and now acceleration equals to m minus m over m plus m times g. In the previous slide we found acceleration. Now let us find tension. So equation 1, t minus mg equals to ma. That is T equals to ma plus mg. Let's substitute acceleration into equation 1. That is T equals to m minus m over m plus mg plus mg. Now let us make the same denominator. M plus m over m plus m. That's actually cancel out. So we tried to make the same denominator by applying m plus m over m plus m into a second section of the formula. Let us distribute mm minus m squared over m plus mg, plus we do the same mm plus m squared over m plus m and g. In this case, the denominator same and m squared cancel out. The denominator same and also they have the same g's, so m squared cancel out. That gives us 2 times mm over m plus m times g. Let us take out the 2 as a common factor. 2 times m over m plus m times g, and that is the tension. Question 2. In figure 2.2, a block of mass m is connected to a small mass m through a string that goes over a pulley. Ignoring friction, find the acceleration of each masses and the tension in the string. The forces are shown in the figure. The acceleration must be same magnitude for both masses, but the larger mass accelerates horizontally and the smaller mass accelerates vertically downwards. The free body diagram on the right taking each mass separately. So let us take a look at a small mass which is accelerate downward direction. That means mg minus t equals to ma. That's our equation 1. And the large mass accelerating horizontally to the right. That is T equals to ma. The reaction force and weight in vertical component cancel out as the object is accelerating only horizontally. And the friction force is ignored in this section. That's equation 2. Adding the two equations, we get mg minus t plus t equals to ma plus ma. T's cancel out. That can be mg equals, we can take out the common factor a. That is equals to a in brackets m plus m. Acceleration equals to mg over m plus m. We found acceleration, which is mg over m plus m. Now we need to find the tension. Let us take a look at the equation 2. In equation 2, tension equals to m times a. We can substitute the acceleration into equation 2. So T equals to ma, which is m times mg over m plus m. And that gives us mmg over m plus m. This is method 1, taking each mass separately. Now we have a method 2, treating the two bodies as one, results in a situation shown. When we treat the two masses one, they have a same acceleration. The net horizontal force on the combined mass m plus m is mg. The object is accelerating as a single entity. Net force equals to m plus m times acceleration. And the net force is mg. And that gives us acceleration equals to mg over m plus m. We can actually substitute this acceleration into second equation. We are able to find the tension as well. A block of mass 2.5 kilogram is held on a rough inclined plane as shown in figure 2.54. When released, the block stays in place. The angle of incline is slowly increased, and when the angle becomes slightly larger than 38 degrees, the block begins to slip down the plane. A. Calculate the coefficient of static friction between the block and inclined plane. The friction force is F, and X component of the weight is W sine theta, as it is opposite. Because the block is about to slip, the frictional force is a maximum possible static frictional force, and so the frictional force equals to coefficient of static friction times the normal force. As a block is about to slip, the resultant force in X component equals to 0. And X component implies here the axis parallel to the inclined plane. Friction force is upward. Resultant force in X component equals to 0 as the object is about to slip. And the X component of the weight is W times sine theta. So friction force minus W sine theta equals to 0. Rearrange. Friction force equals to mg sine theta. As the object is in translational equilibrium, resultant force in Y component also equals to 0. And the Y component of the weight equals to W cosine theta. So as the object is about to slide and is translational equilibrium, resultant force in Y component equals to 0. That is R minus W cosine theta equals to 0. That is R equals to mg cosine theta. As the block is about to slide, the friction is a maximum static friction, and the maximum static friction equals to coefficient of static friction times r. And the question asking the coefficient of static friction, which is equals to friction force divided by r. That is equation 1 divided by equation 2. Mg's cancel out. That gives us sine theta over cosine theta, which is tan theta. And angle is 38 degree. Tan 38 degree equals to 0.78. So the coefficient of static friction between the block and inclined plane is 0.78. B. The angle of incline is increased to 49 degree. The coefficient of dynamic friction between the block and incline is 0.26, which is smaller than the static friction. Calculate the force that must be applied to the block along the plane so it moves up the plane with an acceleration of 1.2. As a block moving up the plane with an acceleration 1.2 meter per second. So resultant force in x component equals to ma. Let F be the required force up the plane. As the object is accelerating upward direction, then the friction force is downward along the inclined plane. And we have the x component of the weight, which is opposite, that is W sine theta. So resultant force are applied force minus W sine theta minus friction, which is equals to ma. We need to find a friction force. Y component of the weight equals to W cosine theta, as it is adjacent. So as the object is accelerating along the slope, resultant force in Y component equals to 0. Object is not moving vertically up or down. That means R equals to W cosine theta. Actually, R and W cosine theta cancel out. And dynamic friction equals to coefficient of dynamic friction times R. And that is equals to coefficient of dynamic friction times R is W cosine theta. Now we can substitute the dynamic friction. F equals to minus W sine theta minus coefficient of dynamic friction times W cosine theta equals to ma. Now we can rearrange and substitute values. F equals to ma plus mg sine theta. Mass is 2.5, acceleration is 1.2, mass is 2.5, acceleration due to gravity is 9.81, sine 49 degree, plus coefficient of dynamic friction is 0.26 times the mass 2.5 times acceleration due to gravity 9.81 times cosine 49 degree. That gives us 25.67 Newton, which is 26 Newton in two significant figures.